Okay, so welcome to the second lecture. So in the first lecture, we have done quite a lot regarding probability distributions. And the reason for doing that was to actually lay a very good foundation of statistics and probability. Because up to now, what we have done in ML1 was somewhat superficial. We did all the algorithms. We also did some basic things regarding time series forecasting. But now we need to build up on our statistical knowledge. Okay, so um, towards the last part of the last class, so we went through some distributions regarding the logistic function and the log normal distribution and also the logit function. Okay, so this distribution and the logistic function itself is very important. So we need to have a very good grasp of its importance and how it works. So today we will be doing that in detail. We will be also solving some numericals in the class to get hands-on regarding logistic function, logistic regression. And then we will be looking at this joint probability distribution in from a childish perspective, so that we develop the concepts. Okay. So let's start now. Okay, so this is what was written in one of the slides in the last class. So the continuous probability distribution means that it is related to a continuous random variable. So random variables can be either discrete or continuous. So that is the basic distinction of the types of random variables. So logistic distribution is continuous, as are many other distributions. Its cumulative distribution function is the logistic function. Now, what is the cumulative distribution function? The cumulative distribution function is actually a function which tells you, if you give it a number, if you give it a value of a random variable, so it tells you what is the probability of getting a value which is either that number or less than that number. So if you give it a number x, so it is going to tell you the probability that the value of a random variable is going to be less than or equal to x. Okay, so that is given by the cumulative distribution function. So and anytime you have a probability density function in the continuous space, so you always have a cumulative distribution function. So you should keep this thing in mind. ठीक है? जहाँ पर आपके पास continuous PDF होगा, obviously it's going to have a formula. It's going to have some parameters. So like we saw in the case of normal distribution, and it is also going to have a cumulative distribution functions, because we want to find out probabilities like this one. Okay, I might ask, what is the probability that some random variable x has a value less than or equal to 3? Okay, so that information is given to me by the cumulative distribution function. Okay, so obviously from the perspective of Python, so it's you just have to call one function and you can get information from the CDF. Okay. So the logistic distribution is actually a continuous probability density function. That's the first thing. And when you plot the CDF of this function, so uski jo shape hai, that resembles the shape of a logistic function. So we are going to be looking at this logistic function in detail because it's very important to machine learning. It is used in neural networks. It is used in logistic regression, and it is also used in other mathematical functions. Okay, so this primarily appears in logistic regression and feed-forward neural networks. So those of you who are taking deep learning, this logistic function is going to be very important for us. Okay? And it is very much, it is in fact an instance of the sigmoid function. There's just one instance of the sigmoid function. Okay. So this is the PDF of the logistic distribution. So the PDF of the logistic distribution resembles the normal distribution. The shape is almost the same, like the bell-shaped curve, but it has higher kurtosis in the sense that the tails are a bit heavy. So the tails has bit, on the high side. You can see you can see some weight there in the tails. So typically when you have the normal case, so it could be something like this. So these things are not heavy. But in the case of the logistic distribution, you can have something like this. So the tails are a bit heavy. Okay, so that's the way it is. So just based on this distinction, it becomes another distribution. Okay, so that's the main thing that you need to keep in mind. All of you do understand, right? PDF, the concept of PDF. Why do we need a PDF? No, Harim. Why do we need a PDF? Why do we need a probability density function? Huh? To find out the probability of a value of a random variable in the case of discrete random variable, or to find out the probability in a particular range in the case of a cumulative or the continuous case. You want to find out the probability. What is the probability that the value of this random variable is going to lie within this range? That is the only reason for making the PDF. And the other thing is that normally the data that is coming in the real world, what I explained to you the last time, the data that is coming in the real world does automatically follow one distribution or the other. Typically, it is always the normal case for the continuous data. But it could follow many other distributions that we saw in the last class, like binomial and Poisson distribution, exponential distribution, geometric distribution, and we also saw the use cases. So that's what you need to realize. That is the reason that we are studying this. Okay. What do you mean by higher kurtosis? क्या मतलब? Yeah, and that's put in a very good way. You have a bit more concentration of data towards the edges as compared to normal distribution, but not necessarily outliers. It does not mean if I have data concentrated in the tails, then we are talking about outliers. No, it does not mean that. So to detect outliers, you need to plot the histogram, you need to plot the box plot, the pair plots, the correlation plots in order if you want to discover the outliers, the scatter plots. So all of these things together can help you analyze what are the outliers in my data. But if data is concentrated in the tails of the density function, it does not mean that these are outliers. It just means the probability of that data is going to be less. Okay, but there is a concentration of data. Wherever there is a concentration of data, you cannot call them outliers. Outliers are typically very infrequent entities. ठीक है, आप आगे आ जाए मेरे ख्याल में. हाँ, जिनको नींद आ रही है ना, नहीं आप नहीं, आप तो मुझे अलर्ट लग रहे हैं. The closer you sit to the teacher, the better it is. For learning anything in the world, not just computer science or machine learning. Try to sit near the teacher. इससे आपको ज़्यादा फायदा होगा. ये चीजें यूनिवर्सिटी में नहीं सिखाई जाती हैं, कहीं और सीखनी पड़ती हैं. आदाब, इल्म हासिल करने के आदाब जो हैं वो आपको कहीं और से मिलेंगे, यहाँ से इन जगहों पे नहीं बताए जाते वो. बहरहाल जी. No, that's not the case. The CDF can have different shape in different situations. For the case of the logistic distribution, the CDF is like this, but the shape of the logistic distribution itself is like the normal curve. That's what you need to keep in mind. Okay? So it is not easy to distinguish between the logistic and the normal, but unless you know the intricacies of the data. Okay? So this is done. Achha, what is this mu and s? Can anyone tell me this? Just make a guess. Eh? Mean and standard deviation. Are you sure? So why it is written here? Anyone आप बताएं? We have three curves here, right? What does it mean? Sorry? Yeah, but I mean, what conclusion do you make? That they have written three variables here, and sorry, they have written two variables here, and there are three colors. So what is the conclusion? What do you infer? Yes, these two are the parameters of the distribution. So every distribution has a formula. That's what I was telling you, Atutala. Or usme there is a formula. It has parameters. By changing the values of the parameters, you can get different curves, but all of them are going to have almost the same shape, the bell curve. Okay. So if you have data regarding the customer call duration and the data regarding the customer age, so both of them might be normal. Okay, but the shape of the curve could be different. So one of them might be skewed, the other might have higher kurtosis or whatever. So in the last class, I told you specifically, I gave you examples that which type of distributions are associated with which types of data. You need to remember those things, so that if you come across these practical examples in your companies, so you will know, this is a Poisson use case, this is a binomial use case, this is an geometric use case, etc. Clear? Is this clear? So don't get worried by this probability density concept. It's a very important concept in machine learning. Okay, and similarly to the density function, the CDF also has a formula because it has a different shape, so it has a formula, and it also has its own parameters. But as it is cumulative with respect to the PDF, so the parameters might be the same as the parameters of the PDF. Okay. So we learned that logistic distribution has a shape which is quite similar to the normal curve, but with a higher kurtosis, and its cumulative density function is actually the logistic function. Okay. Right. So let me just okay. Oh, sorry about that. I just so this is the formula for the logistic density function. You can see that we have mu and s, and you were right that this is the mean and the standard deviation, but it is part of this formula. So this formula is going to give you the probability when you give it the value x. X is the value of the random variable. That's it. It's going to give you the probability. Okay. And so what is s? Standard deviation. Yeah. So typically in these formulas, there might be one or more constants, and there might be standard deviation and mean. I think in this case, it is the standard deviation. Mu is the mean, and s is the standard deviation, and you can get the probability from this formula easily. Okay. The logistic function has this very important formula which you need to keep in mind: 1/1 plus e to the power minus x minus mu over s. In this case, typically the logistic function that we will come across, it is going to have 1/1 plus e to the power minus x. And I think that's the standard logistic function. The standard logistic function. That's it. Like you have the standard normal distribution. What is the standard normal distribution? Nahi malum. Ji. Yeah, mean of zero and standard deviation. Okay, you need to revise along the, as the course goes along. Please find some time to revise what you're doing. Otherwise, how will you learn? Cramming up the material right at the time of exams is not the way to study. Although that's what I did when I was in my undergraduate. That's not the way to study, right? Now I know how the first semester. I'm telling you guys, okay, find some time to study the lecture that day when it finishes, or at least the next day, because then it's fresh in your mind. If you are waiting for the first hourly, then there's no interaction in the class, right? So I don't see much point in teaching then. So please revise at least the other day, or 2 or 3 of you people can revise together also. That will make it easy. So there, yeah, so standard logistic distribution has the formula 1/1 plus e to the power minus x. I think this is also when we have mean of 0 and standard deviation of 1. Yeah, so this is the same case. Mean of 0, standard deviation of 1. standard logistic function, and the standard normal curve. Okay. So what's the use of standardizing the normal curve? Can anyone tell me? See. Yeah, to a large extent, you're right. Anyone else? Why do we calculate the Z-score? What does the Z-score do? चलें, हरीम आप बताएं. So what? क्या फायदा स्टैंडर्डाइज करने? What's the use of standardizing? Sorry? Wrong. Huh? Table. So table to almost all the distributions have a table. You standardize the you standardize the column because of the fact that when you are doing machine learning, then you need to ensure that all the columns are in the same range. Otherwise, one or more columns might influence itself while learning or while doing any other sort of training process. So you need to bring all the columns in the same range. That is the main purpose of standardizing your data. They standardize with respect to the standard normal curve. For example, when we will do cluster analysis, let's say you're recording the age of the customers. So the customers can vary between, let's say, 17 and 83. Okay, and you also have sales. So sales can vary from like 1 rupees to, I don't know, 30,000 rupees. So the range of these columns is not matching, right? The range is different. So if I put this in a clustering algorithm, then the sales column will influence the other columns because of its large values. We do not want that to happen. हाँ, लेकिन मैं कहना चाह रहा हूँ कि with respect to machine learning, that's the use that we make of the standard normal distribution. We can standardize for our own benefit, but even if you are not using machine learning, the purpose to standardize will be still the same, to bring it between 0 and 1 or -1 and 1. You can also bring it between -1 and 1. And there are other scalings as well, min max scaling. So, but the standard scaling works in a lot of situations. Okay. So just keep these formulas in mind. So what is the quantile function? So थोड़ा सा you will have to concentrate. The cumulative distribution function, उसमें क्या होता है? What does it happen? You give it a value x, and it is going to tell you the probability that the random variable is going to have a value less than or equal to x. ये तो clear है ना? Is this thing clear, right? The quantile function is the opposite of the cumulative density function. You give it the probability, and it is going to give you the value of x. Okay, so if you give it a probability 0.25, it is going to tell you the number x below which the probability is 0.25. Understand? If they are just inverse of each other, that's it. That's called a quantile function. Is this clear? And this quantile function is called the Probit function. The Probit function. It's also an important term in machine learning, with a Probit. Okay. The Probit function is the quantile function of the normal distribution. So if you take the inverse of the CDF of the normal distribution, then that's going to be the Probit function. Okay, so just remember this, that one thing we have is the PDF, or the probability density function. Then we also have its cumulative density function, which is going to give me the probability of the random variable taking the value less than or equal to x. And in the third scenario, we have the quantile function, which is, if I give it a probability, it is going to tell me the value of x below which the probability is 0.25. So it's just the inverse of the CDF. Okay, that's what you just need to keep in mind. The quantile is the inverse of the CDF. So in this case, as for example, you can see here we have a value from 0 to 1 on the x-axis because we input the probability in the quantile function, right? So here I can give any probability that 0.7, and the value I'm getting here is 0. Let's say 6. So then that means x less than or equal to 6, the probability is 0.7. That's the for this particular normal distribution. जिसका Probit function निकाला हुआ. Okay, is this thing clear? So just you need to keep this in mind. So the Logit function, why I talked about quantile function, because we want to discuss the Logit function. क्या कहते हैं? Logit कहते हैं, Logit कहते हैं, जो भी बोल रहे हैं. So Americans might be calling it Logit and British might be calling it Logit. और पाकिस्तानी क्या कहेंगे? Somewhere in between. So the quantile function associated with the standard logistic distribution. So the quantile function of the logistic distribution is actually the Logit function. And this is also going to come up later on in our algorithms. Okay. So what is the quantile function of the normal distribution? Probit. So we are given 2 years, not 1. So you need to listen attentively, right? Okay. So what is the quantile function of the normal distribution? The Probit. What's the shape of Probit? Not a bell curve. It's like this one. So it's going to be like that for different. Okay? And the quantile function of the logistic distribution is the Logit function. Okay, just keep that in mind. And this Logit function has many use cases in data analysis, machine learning, especially in data transformations. In many algorithms, this is a very important thing to take care of. Okay. So mathematically, the Logit is the inverse of the standard logistic function. The standard logistic function is what? 1 over 1 plus e to the power minus x. And Logit is the inverse of that. So that is log p over 1 minus p for p in this range. Because we're talking about a quantile function, right? So we have to input a probability. Okay. That's what the quantile is, right? In the quantile, I input the probability and I get the value of x below which that probability is true. Okay. So therefore, the Logit function is log p over 1 minus p when you input the probability. So it maps from probability values to real numbers like any quantile function. The quantile function ka to kaam hi hai ye ki it maps from probability to real numbers, and the CDF is going to map from real numbers to probability, as does the probability density function. Okay. So this is something that you need to keep in mind. So you can see it has a shape which is very similar to the Probit function. Why? Can anyone tell me? Absolutely right. Because the logistic distribution also resembles the normal curve. So there's not much difference in the way it has been formulated. So in the mathematical scenario, in the mathematical arena, so the inverse of the CDF is going to be almost the same function. So the Probit function and the Logit function have this shape, which you should now keep in mind. So now we have two very important things, that the logistic distribution and the normal distribution are very close to each other. And obviously their quantile functions are also close to each other. One is called the Probit, the other is called the Logit function. So they are like two trains which are moving on parallel tracks together. Okay. So these two distributions are very important for us in machine learning. Okay. And now we come to this logistic function. Actually, this is the shape of this is the formula of the. So what was the logistic function? What relationship does the logistic function have to the logistic distribution? Yes, logistic function का जो CDF होता है, that is actually the logistic function. Okay. So I'll just write these things down so that it does not confuse you. Logistic distribution and so CDF is the logistic function, and I don't know what the CDF of this. And we have this Quantile function. It's the Probit, and here we have the Logit. You can see, yeah. So here we have Probit, and here we have Logit. Logit basically we try to make things equal to the log function or similar to the log function because it is easier to control. The log values are lying between 0 and 1. So log function is a very good way to control your data. That is why we take log in many situations. Okay. So is this thing clear? Okay. And one thing also, the logistic function is a special instance of the sigmoid function. They're the same things with different parameters. The sigmoid function, you must have heard about the sigmoid function, right? So we have to discuss the logistic function because it's very important. So it's the CDF of the logistic distribution. And obviously, we can assume the CDF of the normal distribution will also be something close to the logistic function. Okay, but I really don't know right now. So this is the formula that you need to keep in mind. Okay, this is the shape, which is the S-shaped curve. So it's always going to have a value between 0 and 1. The maximum value of the curve is L. Okay, so in the numerator we have maximum value. So when you will see the numericals of this logistic function, you will see where L is used. Okay, so numericals, you can make sense of the value of L. K is actually a decay parameter. So it's actually this logistic function has a history that it was discovered in the 19th century by some mathematician, obviously, to model the growth of population. At what rate is the population growing? At what rate is the population decaying? For example, ants or human beings, or I don't know, rhinoceros, whatever. So this was discovered in 19th century, and they wanted to model how the population is growing. So the rate at which a population grows is not normal. Do you understand? The rate at which a population grows, that actually follows the S-shaped sigmoid curve, and they made the instance of that as the logistic function. Okay. So when this curve was discovered, or you can say when it became famous, it might have been discovered earlier on, but when it became actually famous, so the reason for that was someone wanted to model the growth of population. So therefore, this K is typically called the decay parameter. So I mean, at what rate the population is decaying, or at what rate the battery is decaying for a particular, I don't know, for a particular toy or whatever. So whenever you have some growth or a decay sort of situation, then you definitely need to use the logistic function. And in this case, it has seen many applications in bioinformatics and psychology, social sciences, where you study the behavior of organisms and all type of biological scenarios. So the logistic function is very, very important. Okay. So so the logistic growth rate or steepness of the curve. So because the curve can go in it can go in different manner. Like for example, it could be something like this. So this is not very steep. It could be something like this. So this is steep. It could be something which is very, very laid down like this. So all of these are examples of S-shaped curves. I think we're having a breach of security. Not a breach of security, but we are having a breach of protocol. You're only supposed to be 50% of the seats. All of you are vaccinated, right? then it's a good thing. Okay, okay. Is this thing clear? Do you understand the application of the logistic function? We are going to be having numericals on this in the exam, so please be careful. Okay. Yeah. So the x-axis is not important. So it could vary between -1 million to +1 million. It could vary between -6 to +6. We do not care really. The y-axis is always going to be varying between 0 and 1. That is the plus part of the logistic function. Okay. So, but typically what happens is that you do not need to go towards negative infinity and positive infinity. Okay. You do not need, you just need to focus on the fact that take a small interval of data, like maybe -100 to +100, and you're going to get your distribution in that. You can use the function in a small range of data. You don't necessarily have to go towards negative infinity and positive infinity. Otherwise, how can we manage? We do not have such a big sample, right? As a logistic, the term was coined at that time when this model was first used. And why did they use logistic? Because it looks like a logarithmic curve. So it's something not very similar, but something similar to a logarithmic curve. So they use the term logistic for it. Okay, but it is actually an instance of the sigmoid function, the S-shaped curve. Okay. So yeah. So any questions? If you can ask the questions along the way. Yeah. So one other thing is important. Look at this derivation here. This is one other way to write the logistic function, which is the standard logistic function. 1/1 plus e to the power minus x. I can write this as ex over ex plus 1, and I can write this as this. So this means that basically the hyperbolic tangent function, which is also used in neural networks in deep learning scenarios, it's an activation function. So hyperbolic tangent function is actually a brother distribution of the logistic distribution, because I can express the logistic distribution in the form of the hyperbolic tangent distribution. So the hyperbolic tangent also has the same shape, but just skewed to the left or right with respect to the logistic distribution. So the sigmoid, the logistic, and the hyperbolic tangent, they are all one family, basically, all siblings. You understand? They have the same shape. So do not think that sigmoid is something else, logistic is something else, and hyperbolic tangent is something else. We are referring to the same function basically, but with different parametric values, or maybe some shift there, because you can see you can 1/2 plus 1/2 tan h. So this half is actually shifting the distribution towards the right. It's just shifting it, not even a skew. This is not a skew. It is just shifting the distribution towards the right. So it's starting 0.5 terms away. That's it. I'm just shifting the function to the right, but it has the same shape. Understand? Is this thing clear? So hyperbolic tangent, logistic, and the and what? The sigmoid are basically they're from the sigmoid family. Yeah, so this is what I told you. It is enough to compute the logistic function over a small range of numbers. You don't need to be go towards the endpoints, and except you will reach the saturation even then. And that's what typically happens. So in your usual machine learning case where you are applying logistic regression, we are not talking about logistic regression right now. This is a logistic function. Okay. Even if you have maybe 100,000 of rows, if it's, let's say, 5 to 10 columns in your training data, or maybe you have 80,000 rows in your training data, so logistic function will take care of that, because in one sample of data you don't have all the population, right? So वो जो हमने last time बात की थी कि random variable की एक sample space होती है, you sample from the sample space to get something in the measure space, which is the training data that you see. So you never have everything in the sample space in your particular sample. So it is not a problem in the logistic case of the logistic function. Yeah. So the derivative of the logistic function is the logistic distribution. Now this is one other point which is going to confuse you, because what we have read up to now is that the cumulative density function of the logistic distribution is the logistic function. Okay. But if I take the derivative of the logistic function, it becomes the logistic distribution. Okay, so I've written both these things together. So currently I'm not able to link these two up, but just remember them separately. So if I take the derivative of the logistic function, I will get a normal curve. Okay, and if I take the cumulative density function of the logistic distribution, I will get the logistic function. It will have something to do with that. Derivative, what is the derivative? Rafi? Derivative क्या होता है? What do you mean by computing the derivative of y with respect to x? अभी मैं उनसे पूछा. हाँ? Sorry? Denominator का change. जी, who else? हरीम आप बताएं. Yeah, so what do you mean by dy over dx? What does that mean? What do you mean कि change देख रहे हैं? इसका क्या मतलब है? How is y varying with respect to change of x? Make it more explicit. What is the pattern of y changing itself when I change x? How is y changing when I change x? What happens when I increase x? What happens when I decrease? What happens to y? That is the derivative. So the derivative of the logistic function is the logistic distribution. So it happens that when I apply the derivative of each point here, but the values that I'm going to get are going to follow the normal distribution, or in this case, the logistic distribution. You remember from the last time we read about this central limit theorem. What is the central limit theorem? What converges to the normal distribution? The mean or the average or the sum. That is the thing. So it might be different parameters, but typically we talk about the mean. So the mean of many different samples of a random variable will converge to a normal distribution if you take a large number of samples. And that is the information that we use in many engineering and industrial applications. That distribution itself might not be normal, but the mean over a large number of samples is definitely going to follow the normal distribution. Okay. So this is a bit of maths. I don't know what this is about. Yeah, so we are deriving the formula when I take the derivative of f of x. That's what we are saying, right? When I take the derivative of the logistic function, it converges to a logistic distribution. So that's like a normal curve. So the equation that we have written here, this equation is very similar to the equation of a normal curve. So if you have a graphing calculator, you can plot it and it's going to show you something like a normal curve. Okay, is this in clear? So please remember what we have written here, and also what we are writing here. The derivative of the logistic function is the logistic distribution. So I can just write it here. D over dx function equals to the logistic distribution. Okay. So that's the main thing. We'll take a break in some time. Namaaz ka break abhi lenge. So just wait azan ho jaye to phir just wait 1 minute. So this is okay. So this is above. This is the function of the standard normal distribution. Standard logistic distribution is in terms of hyperbolic tan. This is just a derivation that I took from the net to understand myself how we derive actually. I mean, when we take this derivative here, how we come to this function. Okay. So these are just the steps. You take it up. So when you take the denominator up, so you get -1. And I can write this as this one because -2 + 1 is -1. And I take the derivative on this side because I can, move the derivative. And then I take the derivative of the internal term. So it becomes like this. So 1 is just, it becomes 0. There's no derivative there. And then I have e minus x. So derivative of e minus x is what? Minus x ex, right? No, derivative of ex is ex. And minus x, yeah, so derivative of minus x into ex. So derivative of minus x is with respect to x is just 1. So that becomes minus, and then blah, 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 blah. So in the end, this becomes the numerator and this becomes the denominator. So that's the equation of the normal curve or the logistic curve, which is like normal curve equation is different, obviously, but you will find lots of similarities if you look at it mathematically because the shape is almost the same. Okay. So the main, are you able to guess why this curve is important? Are you able to guess why this curve is important? The logistic function curve or the S shape, the logistic function. Why is this important? In what way? Where? Where is the boundary? It's a continuous function. Huh? Where is the boundary? I don't see any boundary. We're talking about the boundary of a cricket field, so I can see the boundary there, right? There's no boundary here. Let's forget about the classification part. Okay. Just what is the most important application of a logistic function when you look at this curve?
Sir, we can calculate the growth, just like you have mentioned, the growth of population.
Growth? No, that's not the answer. That's the answer for, okay, on a side track that could be true, but that's not the answer that I want. Gee. Yeah, that's not the answer, but that's a good observation. The probability is converging towards 1 when you go towards infinity, and the probability is converging towards 0 when you go towards negative infinity. That's the observation. But what is the use of this? Why it is so famous? Because it is able to map everything into a probabilistic scenario. For example, if you are detecting the objects in an image, and you just do not want to detect the objects. You want the system to say that I have detected this object with a probability of this. I have detected this object with a probability of this. And the sum of all probabilities should sum to 1. For example, in an image, we have a car and we have a tree and we have a dog. Okay. So it could say that it is able to detect 3 things. So I've detected this car with a probability of 0.6, tree with 0.3, and dog with 0.1. Or if each object has its own probability density function, so the probability of each will vary between 0 and 1. So then that gives me more confidence that it has detected this object in a good way or not, rather than saying I've detected this object, rather than saying this is the class label. Not just in the simple machine learning case, I can say, give the loan to this customer. So how much confident you are with respect to, let's say, like we discussed the confidence interval last time. What was the use of the confidence interval? Can anyone tell me? Zan? Confidence interval का क्या फायदा है? जी. Yeah, so the confidence level tells you that with what level of confidence you are able to say that the value is going to lie within this particular range, and we can estimate the range from sampling. We have a formula to calculate the confidence interval, and you should know that formula because you need to calculate. Just need to know how to calculate that. Okay? So the main thing is that in the case of machine learning, when we output the class label, we can couple that up with the probability that the class label is true with a probability of 80%, and it is false with a probability of 20%. So then that gives you more confidence that yes, the label is yes. Okay, so this is why the logistic function becomes very important also in deep learning, because in the deep learning, when we are recognizing objects in an image, so in that case, I must know the probability of the confidence that the system has in detecting the object probability, or for any other machine learning problem. Okay. So let's go ahead. Yeah. So we are just taking it onward from there. So this is where we stopped in the last slide. So the derivatives, I just continue to change its notation. I can write it like this, blah, blah, blah. And in the end, it becomes something like this: 1 minus f of x dot f of x. Okay. So the derivative of the logistic function can be written like 1 minus the logistic function dot the logistic function, which is 1 over 1 plus e to the power minus x. So this is a standard way of writing the derivative of the logistic function. You will find this on many websites and probably in some books as well. Okay. So the derivative of the logistic function is what? The logistic distribution. Okay. So the logistic distribution can be written in this way: 1 minus f of x dot f of x, where f of x is 1 over 1 plus e to the power minus x. Clear? Okay. Practice questions. So we know. So get ready. This is an online quiz, real-time quiz. ले ले, इसी पे नंबर लगा दूं मैं. हाँ? आप दोनों ऐसे करें, आप में से एक उठ के इधर आ जाएं या इधर आ जाएं बीच में, ताकि आपस में बातचीत ना हो ना. I want to minimize the noise in the data. Okay. Literally or figuratively or whatever noise in the data, I want to minimize that. And आप इधर be careful, आपको भी order आ सकता है अनकरीब. ठीक है. Okay. What is this function? What shape does this? What does this function represent? Sigmoid. I mean, we have just done the logistic function. So let's talk about the logistic. It's from the sigmoid family, right? So let's assume it's a logistic function. Okay. What is the carrying capacity of this function? Carrying capacity, what does that mean? What could it mean? Yeah, it could mean the maximum value that this function can have. So what is the maximum value? 23. Are you sure? What's your name? Sorry. Talal. So Talal is right. 23 is the answer, because I told you that L is the maximum value that the function can take. I told you a few slides back. Online वाले भी please जरा होशियार रहें, ठीक है? A pot is filled with 128 ounces of water. The water is slowly evaporating by 2% per day. How many days will it take until only 18 ounces remain? This you don't look at this function. Okay, think about the logistic function. This is only for a separate question. How will you design the logistic function here? आ जाए बोर्ड पे आके सॉल्व करें. Who is going to take the initiative to solve it on the board? Anyone? You're afraid of numericals. Let me just write down the basic equation that we have. So f of x equals to 1 over 1 plus e to the power minus x. Now if you want to put it in terms of variables, L over 1 plus a e to the power x minus x naught. Okay, so I'll just write it down here so that anyone can see it. Yeah, so okay, so I'll just use this. मुझे नहीं मालूम, न्यूमेरिकल्स तो आप लोगों ने सॉल्व करने हैं. L over क्या था यार, 1 plus e to the power minus k x minus x naught. What is x naught? The central, the midpoint. It is the midpoint. X naught is the midpoint of the whole application that we are considering. So now solve this from this equation. How many days will it take? Remember, this is not a probability density function. We are not calculating probability. This is a function called the logistic function. So I want the value of f of x. And maybe it could also ask something else, but this is the function. And k is what? Steepness of the curve, growth rate. K is the growth rate on the positive side, okay? Now tell L kya, what will be the value of L? 128. K? Yeah, K is the growth rate on the positive side, but here we are talking about the evaporation. It's on the negative, so it's going to be minus into -2, which is 2. Yeah, 0.02, yeah. And what is X naught? No, X naught is a constant. ये क्या लिखा हुआ X naught? The sigmoid's midpoint. So what will be the midpoint here? क्या है? So MT 101, CS 101, और क्या है वो MTS 101? 64. 128 is the maximum, right? The midpoint is 64. Khatam. So 128 over 1 plus e to the power 0.02 into 18 minus 64. That's going to be the answer. You are just required to plug in values. Don't think about the curve right now. The curve is always going to be S-shaped curve. Okay? Is this in clear? So to calculate this, you need your scientific calculators in the exam. हर चीज का जवाब देना जरूरी नहीं होता. LMS बाजू पर काफी हो जाता है. E to the power minus x, this function written there, right? So you are allowed to bring your notebooks or whatever. So online, you can also do this online calculator. अगर आप करते हैं mobile पे भी, you can use the mobile. Okay. So for this exam you might have a online exam as well in the hourly case. So we could choose that.
Sir, whiteboard is not visible.
What is not visible?
Whiteboard.
तो वो तो नहीं होगा ना visible. Obviously, वो कैसे? How can I make that visible here? I'm not writing that much. I'm just telling you how to calculate that from the oh, sorry about that. I just said कि e to the power minus x is something जो calculators के ऊपर is written e x. So you first type in x and then press e, so it's going to give you that value. Okay, so it's pretty simple. Solve this one now. That will produce a height of 9. So how will you solve this? So that is going to be 9, 1 plus 7 into 0.05 to the power of x equals to 22. ऐसे ही है ना? Then let me take 22 over 9 here. And then 22 over 9 minus 1 here. Okay. I'm just shifting to the other side because I have to solve for x. And divided by 7. Divided by 7. Okay. Now what? कौन सा log? Natural log. You take the ln. When you take the ln, then you can bring the power down. So x will be ln of this divided by ln of 0.05. That is going to be the answer. Okay? So it's just It's just a practice to help you get on track, nothing else. What is the y-intercept of h of x equals to this? It's a function, right? So it is going to have a y-intercept. Yes, बिल्कुल सही है. तो बताएं क्या होगा? 25/9. Simple as that. ठीक है. Next, जल्दी जल्दी शाबाश. Just tell how it's going to be solved. आपका नाम मैं भूल गया. Arslan. It's a childish question. Do you have to find PT or T? You have to find the value of T, right? And what is PT? Huh? Will you use the value 4 billion here or not? 4 हो रहा है use. So what will you do? 50 equals to this and find out for T. Is that it? Are you sure? Exam में देखेंगे क्या होता है. ठीक है. Okay, so what I will follow this solution जो आपने बताया, because I think that's what it is. Because T, whatever the value of T comes, it's the number of years since 1976. So let's say it is 180. So you will add 180 years in 1976 and then give the answer. Okay. See, given the carrying capacity is 24 and 2 points, write the logistic function that represents the given situation. Yeah, so how will you solve it? L is the value 24. What is x naught? 12. X naught is 12. So you have to solve for k. You have to find out the value of k actually. So you are given 2 points. Taral is right. You're given 2 points, and using those 2 points, you can find out the value of k. It's just simple maths. You have 2 equations with k's. You can use one within the other to find out the value of k. ठीक है? या नहीं? I think even 1 is enough, because we are given 3. We are given the value of x. We are given the value of y. We are given the value of L. So even one of them is enough to find out the value of k. Write the logistic function. You just have to find out the value of k. Huh? ये y है ना 3. That is f of x. अच्छा, you have to use, I think, this point 1,9. दोनों use कर सकते हैं. Let me try to solve it. How to solve for this? We take ln. Yes. Ln of e is just 1, right? So 2k equals to 7. So in this case, k equals to 3.5. So but we need to try it out with the other one as well. 1,9. I don't know what will happen with respect to that. 9 equals. Sorry? हाँ हाँ ठीक है ln 7/2 सही कह रहा है. I don't know whether it's going to give me the same result. 9 equals to 24 over 1 plus e to the power minus k. It's 1, right? 1 minus 12. So this is equal to 9, 1 plus e to the power minus k minus 12k. Yeah, I don't know. इसको सॉल्व करके देख लें. ठीक है, we can't go into that much detail. तो इसको आप लोग सॉल्व करके देखें. Basic concept you understand, right? Those who are online, just remember that if we have equation like this, 2 to the power x equals to 9, then to solve for x we have to take ln, natural log. When we take the natural log, then x will become x. I can bring it down then by taking the natural log. So that is ln of 9 over ln of 2. Okay, just keep this thing in mind. Baki you can solve even if you have e to the power 2x. So ln of e is just 1. So 2x I can bring it down. Okay. Okay, so what about these one? Jaldi kar le. Given the carrying capacity is 24 and 2 points, it's the same thing. Okay. Given a carrying capacity of 50 and 2 points, again it's the same thing. So you just need to try out both of them. I don't know what's going to happen. The amount of ants in a colony F that is decaying can be modeled by f of x equals to 800.87 over to the power x. ध्यान रखिएगा जरा. This is an exponential function question, where x is the number of days since the decay started. By what percentage is the colony decaying? 87%. That's the correct answer. Because the okay, I'll do that. Okay, I'll do that. So the rate at which it is decaying is 87%. So that's the you can understand, because it's 0.87 to the power x. So everything is going to be with respect to that. You have to put the decay rate, okay, with respect to the number of days. You have to bring in that factor. The expression 12 into this models the population of elephants in a wildlife refuge after T years since 1975. What does the value 12 represent? Very, very simple question. The population of elephants is given by this when T equals to 0. That is the population in 1975. Khatam. 12 का answer कब आएगा? When T is 0. Because anything to the power 0 is 1. Right? So you just put T equals to 0. That means 1975. What was the population in 1975? 12. That's it. So just need to be a bit innovative. It's not very difficult. What do you see here? No, there are two things.
Sir, in linear regression, we are trying to fit the line, the best fit line. And in logistic regression, we are classifying it.
Yeah, that's true. Usman Khan. उस्मान खान जाग रहे हैं? तो शायद नमाज के लिए गए हो. रबना आप नहीं? आप?
Yes sir, I'm here. Sorry, yeah, I'm here.
जी बताएं, ये आपको ये क्या नजर आ रहा है इसमें?
सर ये एग्जैक्टली ये लॉजिस्टिक रिग्रेशन जो सेकंड वाला है, इसमें तो क्लासिफिकेशन ही हुई भी है, और फर्स्ट में दे आर ट्राइंग टू फिट इन के सारी चीज फिट हो जाए.
They are trying to show basically that it is useless to use linear regression for classification tasks. So ये तो when you have the label which is with values close to 0 or 1, I might have a label which has values close to 0 or 1. So it's better to, I'm talking about numerical values close to 0 or 1, right? So I might be tempted to use linear regression for that, but it might not be a good solution. So in that case, it is better to use the logistic regression scenario. It's called regression because we are trying to still fit a line, but we are trying to fit a line with respect to the S-shaped curve. Okay. So logistic regression is a very, very important algorithm in many applications. For example, to predict whether an email is spam or not. This is one of the more famous use cases of logistic regression. Even Bayesian algorithms have very good results on this particular problem as compared to random forest or whether the tumor is malignant or not. That's an extremely critical question for doctors. Yeah. We need to bound linear regression between 0 and 1. That is the main point. That is the linking point in this case. Actually, we are doing a type of regression, right? But we need to bound it between 0 and 1. We will do that by using the logistic function. Okay. But this logistic regression is modeled as a classification task. Okay, it's not modeled as a regression task. And now you have to understand what happens from the inside. Okay, there's always a hypothesis. What is a hypothesis? I think I told you that in ML1. When you do machine learning, you always have a hypothesis space. What does that imply? What's your name at the back? बताइए आप. नहीं मालूम. Who knows? देखिए 3 लाइनें हो या 10 हो, कॉन्सेप्ट नहीं. Not exactly. Eamon, you should be able to answer this. Huh? Why? And I don't understand what you're trying to say. Okay. I'm trying to ask, what do you mean by the concept of a hypothesis in machine learning? What for what? Belief for what? To some extent, but I'm asking with respect to machine learning. Harim, aap bataएं. I think you're linking it up with inferential statistics case, but I'm talking about the hypothesis concept with respect to machine learning, not null hypothesis or alternate hypothesis. It has nothing to do with that. Yes, I think you are very near. Hypothesis is actually our. There are many different possible solutions for splitting up the data. अगर हम classification की बात कर रहे हैं, so I can break up the data in many different ways. For example, by using a straight line or by using a triangle, by using the equation of a plane, for example. So I want to separate the data for a classification task, right? What's the purpose of classification? To separate the data for two classes, to learn the equation of a decision boundary. That's what we are looking for, right? We want to split, we want to find the equation of a line or a surface which is able to distribute or separate the two different types of data points, or three different if you have a multi-class problem. You know, is this clear, right? So hypothesis is exactly that. What is the equation of that line, or what is the shape of that surface or line that is going to do this separation? So I have different hypotheses. So the data could be separated by a straight line. It could be separated by a plane or a hypersurface. It could be separated by a convex function. What is a convex function? I think convex function is something which is, Amen, something like this. And a non-convex function is something like this. All of these are hypotheses. So my data could be split up by any curve or any surface or any different line, and I don't know what that is. So that is the reason that we have to try out different machine learning algorithms, because we do not know what is the hypothesis. हमें नहीं पता कि वो हमारे जो classification data को कौन सी चीज जाके काटेगी. So sometimes we are trying neural networks, sometimes we are trying logistic regression, sometimes we are trying SVM, sometimes we are trying XGBoost, because we don't have knowledge of the hypothesis. This is the reason that we have to do trial and error. So अगर हमें यही नहीं पता, बस हमने कहा कि भाई template बना के चला दो उसको, you must understand the concept, right? There must be a difference between you and any other person जिसने online पढ़ के सारी चीजें सीख ली है. So you need to understand machine learning with that perspective. अगर आपसे कोई पूछ ले भाई ये क्या कर रहे हो, तो what will you say? वो towards data science के ऊपर मैंने 10 blogs पढ़ी थी, वो सारे यही कर रहे हैं. So that is not the answer, right? You must have a reason for what you are doing. I take most of the material from blogs, Vidya और ये सारे जो हैं machine learning mastery, but you must understand what they're saying. What's anyone can copy, a 10-year-old kid can copy that. Understand? So output is 0 or 1. Hypothesis Z equals to WX plus B. What is this? And what's up? So what is X? The random variable. Okay. B, the bias. Absolutely right. W, weight. So where have we seen these things? In the neural network. So you see the relationship between neural network and logistic function. They are very close to each other. But here we don't have neural networks. But what we are assuming is that in logistic regression, the hypothesis is that the separating hyperplane is going to have this function. Because इसका क्या मतलब है? इक्वेशन को यूज करने का क्या मतलब है? What's the inference from this? अगर मैं कहता हूँ कि यार मेरा separating hyperplane ये है, मैं force कर रहा हूँ कि यही है, what's the conclusion you can make? That my data is biased? Sorry? Linearly separable. That's the answer. Because I'm separating the data by a straight line. This is the equation of a plane or a straight line, but it is a straight. It could be 2D, 3D, 4D, 5D, whatever, but it is a straight line or a straight plane. So then that means that my data is linearly separable. I don't need to have a convex function or a non-convex function to separate the data. So that's the assumption that we have in logistic regression. That's good. Okay. Obviously, when I get the value of Z, then I put that in the sigmoid function to get the actual value between 0 and 1. समझ में आ गई बात की? After I find Z equals to WX plus B, जो कि I'm also finding in neural network, then I put that value in the sigmoid function or the logistic function to get the value between 0 and 1 so that I can, बताएं? So that I can do what? Classify तो Z से भी हो जाएगा. Why do I put it between 0 in the sigmoid function? Yes, to get the probability and also to classify. I'm sorry, मैं इसको गलत ले गया. Also to classify if I have a threshold. For example, I can say if the sigmoid value h theta जो भी यहाँ लिखा हुआ है is greater than 0.5, then the class is 1. And if the value is 0.6, मैं कह सकता हूँ कि if the class is 1 with a probability 0.6, and obviously class is 0 with probability 0.4. एक तरफ की निकालनी है बस, ये बाइनरी क्लासिफिकेशन प्रॉब्लम. ठीक है? हाँ, अभी है टाइम. बहुत टाइम है, चलते हैं बस अभी, नमाज मैंने भी पढ़नी है, मेरे पे भी फर्ज है, बस ये just finish this, ठीक है. So you write it like this: h theta x, which is the sigmoid function, is you find out these two probabilities: probability y equals to 1 given x, and the parameters of the logistic function, or the parameters this. ये theta यहाँ पे क्या है? शाबाश, जल्दी जल्दी. Absolutely right. Theta means w and b. That are the parameters that I have to estimate. So whenever you run logistic regression, you are going to estimate the values of w and b from the training data. And when you estimated them, then you're going to test the model using the testing data. Okay, that's what happens at the background. So this is what we have talked about. So you find out these two values by using the sigmoid function. Sahi hai? Okay, online people were taking a break now for prayers. Okay, so we are back. We have to move quickly now because. Okay, so in logistic regression, we can try to predict binary, the binary normal case that we have. Multinomial is also possible. I can have more than two class labels, and I can also have ordinal in the sense that ranking based variables 1, 2, 3, 4, 5. So a rank could mean something. To predict which class a data belongs, a threshold can be set. Because without a threshold, how can we distinguish between 1 and 0? If it is a value, if I come up with a sigmoid value of 0.4, so it is logical to assume that I have to take it towards the class 0, right? So I have to set a threshold. So that threshold is typically 0.5. If it is a value greater than 0.5, then I take it as class 1. Otherwise, I will take it as class 0. Okay. But I can also change this threshold. Do you know where this changing of threshold is used in machine learning? I have the, if I have a 0.5 threshold, that seems to be a normal way of classifying things, right? But if I set the threshold to 0.2, what does that mean? एक मिनट ठहरो मैं जरा. जी, Usman Hassan, are you there? Yes, sir. अगर मैं threshold को, if I take the threshold to 0.2, what would it do to the classifier?
सर उसकी फिर रिस्ट्रिक्शन बहुत ज्यादा होगी, तो बहुत जो प्रेडिक्शन होगी वो उसको.
The answer is wrong. जी, who else? I'm not. What is going to happen to the classification? Yeah, but that's what I'm asking. What is the complication that is going to happen if I set the threshold to 0.2? False positive. ये कहाँ से आ गए? So what will happen? A majority of the data will be classified as positive. A majority of the data will be classified as positive, leading to false positives as well, and some other problems. And if I set the threshold to 0.8, then what's going to happen? The opposite. The majority of the data is going to be classified as 0. So why would I want to do it? Who talked about fraud? I'm just asking a general question. There's no concept. Fraud कहाँ से आ गया? जी. Yeah. So now you're in calm waters. ठीक है? कि पहले तो तूफान आया होता ना. No one was able to do anything. So I might need to shift the threshold based on the machine learning application that I have. So for the case of fraud, I might decide to push it above 0.5. Because if I push it below 0.5, then many non-fraudulent cases will become fraud, which I don't want, because I know that fraud is very infrequent. So I might push the threshold to 0.8 in the case of fraud. And in the case of some other scenario in which I want some space, I can push the threshold down to 0.2 or 0.5. So that means that for any machine learning application, I should have this flexibility. How can I get that? Eamon? You should be able to answer this. D. How can I get this flexibility? क्या मैं करूं कि I get this flexibility कि I have an idea of my classification performance based on different thresholds. What should I do? और आसान सा सवाल है, ज़्यादा मुश्किल नहीं है. I'm saying कि what we have discussed right now, we saw that there could be a need to change the threshold, right? For a given machine learning application, there could be a need to change the threshold. What we are doing right now is by assuming by default 0.5 for every machine learning problem. So what is the performance metric that I need to use to ensure that I have the classification performance, which is based on different threshold selections? I want the algorithm to select different thresholds and then perform, because that is the only way the algorithm will be able to perform robustly. Do you understand my point? हाँ, मैं वही कह रहा हूँ कि what is the name of that evaluation process? Hyperparameter tuning is for learning the parameters of the algorithm. We are talking about the output of the algorithm. हाँ, आप ट्रेन में बैठ गए हैं, but we have not reached the destination. Okay. Yeah. Cross validation. You should know cross validation like the fingers of your hand. हाँ, तो yes, yeah, she has hit the. हाँ, तो मैंने इसलिए आपसे कहा कि आपको जवाब देना चाहिए, ठीक है? So ROC curve is the you can say an output curve of the classification process, which gives you an idea of the performance of your classifier based on different thresholds. So it evaluates your threshold, it evaluates your classifier over different thresholds of the logistic value of the logistic function. 0.5, 0.4, 0.3, 0.2, 0.8, 0.9, and then it determines the performance of the classifier. So you get a very clear idea of the performance of your classifier based on the ROC curve. Okay? The ROC curve typically goes like this. Abhi iska assignment, I'm going to give you the assignment for that. You're going to do it yourself. The code aapko online mil jayega. Try to understand yourself. Make a sort of a lab for an ROC curve, a use case application. Okay? I'm going to tell about that later on. In the credit scoring case, in which in the credit scoring case, we have to generate the probability that each customer is, what is going to be the credit rating of each customer. Or in other cases, for the marketing case, what is the probability that this person is going to respond? So in that case, logistic regression is essential, because based on those probabilistic outputs, you can sort the customers and select the top 10 ones or the top 20 ones. So yes, it's one of the things that in which you can use, and you might need an ROC curve. The ROC curve is exactly like this, the S-shaped curve. Okay, and when you have this box, so it's the average performance is the y equals to x line, and if your ROC curve goes like this, something like this, it's a part of an S curve, you can say. The more closer it is to the value of 1, the better it is. So your assignment would be to read upon this ROC curve and then make a lab A small lab, not too much, not a big lab. Also, one thing is regarding the quizzes, we might not have quizzes in the class because we have some people online. So I will give you the quiz, and the time for the quiz is going to be 1 day. The time for the assignment is going to be 1 week or 2 weeks, or if you want an extension. I won't be that much strict as in the case of ML1, but quiz may, you're going to get 1 day for that. You have to do it yourself online. And if you cheat, then you will definitely regret it in the hourlies. Okay. So try to solve it yourself. And we'll try to discuss that at the end of the class. Okay. I know it's at cities, it's probably better. Okay. So we'll discuss this at the end of the class. Okay. We'll see. So, so if the predicted value is greater than 0.5, then predict it as spam. Otherwise, it's not spam. Decision boundary can be linear or non-linear. Where did that come from? Huh? Polynomial order can be increased to get complex decision boundary. So it is possible to get a non-linear decision boundary as well. But in the case of z equals to wx plus b, if that is the hypothesis, then it's a linear use case. What is the cost function in regression? राफे आप बताइए. What is the cost function in a machine learning scenario? What is the cost function? We did regression, right? We did linear regression. Cost function क्या होता है? It's a very simple question. Loss function, cost function, error function क्या होता है? हरीम बताइए. SSE, what's that? The difference between the predicted value and the actual value. So what is the use of calculating the error in a classifier or a regression scenario? So how do you use that error? That's a separate thing. The error term is going to converge to the normal distribution. I think that's what we did, right? I just told you in the last class. The mean error will have a distribution which is equal to the normal, or the error terms themselves are going to converge to a normal distribution, and we can use that information somehow later on. But how do you actually use the error to train the classifier? Yes. So the loss that is obtained, actual minus predicted, that is used particularly in the case of this neural networks in backpropagation. So you backpropagate the error to readjust your weights and biases. That's what you do. You backpropagate the error to readjust your weights and biases so that the classifier will learn, अच्छा यार मेरी ये गलती थी. ठीक है? Oh, this is the mistake I made. So let's learn from that. So you do that either at each instance, or you do that after a batch of data. You can do both. So for example, you can input, let's say, a batch of 100 instances, 100 rows, and then do the backpropagation to train the classifier, or you can do that on each particular instance as well. So that's the stochastic gradient descent process, SGD, in neural networks. So deep learning, we're going to do that in detail. ML1, we did not do that in detail, backpropagation. So we'll try to somehow force it in this course somewhere. थोड़ा बहुत अभी कर लेंगे. अच्छा. So what is this cost function telling you? Can you tell me this? What is this? For the class, positive class, the loss function is minus log of the sigmoid function. And if it is the zero class, it is minus log 1 minus the sigmoid function. So the cost function of the logistic regression classifier is defined as this. It is not the sum of squared error, जो कि हरीम अभी बात करी थी कि actual, because we have labels. We do not have numbers at the output. We have labels 1 or 0, right? So this is how we calculate that. So remember that this is the loss function for the logistic regression classifier. Okay. इसके बारे में और भी हम देख रहे हैं. So this is I took this from an online source. So this is explained pretty clearly. So you can see what is written here is the cost function h theta x is the output of the sigmoid function. That is the output of the logistic regression classifier. Y is the actual value that we want to compare with. So y is the actual and h theta x is the predicted one. Okay. And this is exactly the loss function that was written in the previous slide. Okay. So basically what we are saying here is that the method to find out the loss is different for each class. So yeah, that's in the case of binary here, when you have two classes. When you have three classes, then it could be an extension of this. It is possible to have more than two classes. Okay. I think it might, what it can do is that what we do in the binary +1 or binary +2 case is that we merge the other classes together. So what it can do is it can find out the loss for one class. For example, y equals to 1 is one class, and consider the loss for all the other classes together. And similarly for each, it can separate them. Okay. But one of them is going to be the positive class always, because we are thresholding with respect to the positive class. So I think we have to formulate the problem in a different way when we talk about more than two classes. So इसलिए आपको किताबों के अंदर mostly you get the binary because that's the most simple one. To try to avoid the tertiary case. ठीक है. So you can be a bit more innovative and try to understand that either we can have more than one threshold, because the scenario in the logistic regression is that I always have a positive class. So one of the three is going to be the positive class. Or what will happen is that each one can be the positive class and the other two can be the negative classes. So the cost function is going to remain the same. But the cost in minus log 1 minus h theta x is going to be the loss for the other two classes together. Understand? So if y equals to 1, so this is how you design it. Minus log h theta x is going to be like this. This is the function, because log of z is obviously like this. It's a curve like this, and minus log is the inverse of that. So minus log h of theta x is going to be like this. Okay. Yes, sir. Just for your knowledge, just keep this in mind. Okay. At most, agar iska sawal aaye bhi, to I'm going to give you multiple choice questions. So it's not a big problem. You just need to understand, remember these things. This is the case for when you're talking about the positive class, right? And in the positive class, if the cost is 0, what do you mean by cost 0? There is no error. So what should happen? Why? When will that happen? Y equals to 1. If h theta x equals to 1, then the cost is 0. 1 and 1. You know, for the class, we're talking about the positive class, right? So if the value of h theta x is 1, then the cost function is going to give you the value 0. So yeah, that's and infinity cost when h theta x equals to 0. So I wanted to predict the positive class, but it is giving me output 0. So it's extremely far away from the reality. So then that means the cost is infinity. Because you know, in the logistic function case, we are going towards either positive infinity towards the one side. The number 1 के करीब जाते जा रहे हैं. Negative positive infinity में चले गए x की value. Negative infinity में आप 0 के करीब, you are coming closer to 0, but never actually reaching 0. Okay. So just remember the function log z goes like this and inverse log z goes like this. So in both the cost functions, we have the inverse log z. So it's going to be the other way around. Okay. So minus log 1 minus z is going to be like this. ये जो function है red, this is the shape for minus log h theta x. Okay, and this is the shape for minus log 1 minus h theta x. So the loss function for the positive class is like this, and the loss function for the negative class is like this. So just keep this in mind that there are two different functions which have their own shapes. And when the cost is 0 for the positive class, it means that the output of the sigmoid function is 1. If the cost is 0 for the negative class, it means the output of the sigmoid function is 0. So if you plug in the values, वो आपको 0, 1 अपनी जगह पे मिल जाएंगे. Just remember this. Just remember the shapes and the this cost function. Okay. So this is what we are writing here. So I can write it combined in this way because I don't want to write two different things. So if I want to combine both these two things together, both the cost together, so I can write it like this: minus y log of this minus 1 minus y log 1 minus h theta x. So this is the combined log cost function for both the classes. So even for the positive class and negative class, I can use the same function. So if y equals to 1, then 1 minus y term here will become 0. Therefore, minus log, it is going to converge to minus log h theta x. And if y equals to 0, then it is going to converge to minus log 1 minus h theta x. सही है, तो मैंने सिर्फ दोनों functions को combine करके एक general function बना दिया. That's it. So if I ask you to do, if I give you some values in numericals, you just have to use this formula to find out the cost. सही है? Is this thing clear? So just to practice, you should understand that the cost function of logistic regression is different from cost function of artificial neural networks and normal linear regression. Okay. So this is something which you don't need to concentrate on. What is happening here? I simply forgot. So y dash is the predicted value, which is equal to the probability of y equals to 1 given x. And if I do, so 1 minus y dash is the opposite probability of that. Okay. And if I do probability of y given x, if I want to combine both of them together, because I don't want to write two different conditional distributions. This is a conditional distribution. ये तो पता है ना सबको. Probability of y given x is a conditional distribution. We'll do that in more detail later on. If I want to combine both these things together into probability of y given x, so y can be either 1 or 0. Similarly to how we have combined power. I think क्या ऑफिस का काम तो नहीं कर रहे? हाँ ठीक है. In this here, I have combined the cost function. Similarly, I can decide to combine these two conditional probabilities into one conditional probability. So I can write that as, if I combine these two, then I will have to convert that to this format. You don't have to remember this. Just keep in mind that I can write a combined notation. Okay. So in this case, अगर y 1 हो जाता है, तो it converges to this one. If अगर y जो है वो 0 हो जाता है, it converges to this one. And when I take the log of this, अब आपको logic समझ में आनी चाहिए. What I'm trying to say. What does this mean? Probability of y given x. I'm given the training data or the test data, make a prediction. What is the probability of that prediction? Y is the prediction, right? So I'm saying it is equal to this. When I take a log of this probability, in fact, okay, so that actually converges to the loss function. So what does that tell you? Log of the conditional probability. Basically what I did was I wrote this conditional probability to join these two. ये तो बात समझ में आ गई है ना? If I have to join both of them, then I have to use some formula, some chain rule or addition rule based on y hat and 1 minus y hat. So I have to write it like this. Now when I take the log of both sides, what happens? Log of this is this, which is actually the loss function. So probability of y given x, log of probability of y given x is the loss function. What does this mean? Loss function is the cost, right? Is the negative cost, in fact. इसका क्या मतलब है? You got millions of billions of neurons in your mind. So at least use 5 or 10 of them. Huh? We're talking about neural networks, so I'm giving the same example. Yeah. Ye actually probability of y given x is the likelihood function. It's a representation of the likelihood function. Ke give me the values of x, for example. Likelihood function means ke I want to find out the values which are going to maximize the chances of getting a positive class. Maximum likelihood estimation, may you use this term. We call it the log likelihood. Okay, so basically, if I am what does this minus term represent? If I am decreasing the loss, I'm increasing the likelihood. That's what the negative sign means, right? Agar loss mera kam ho raha hai, it is making the conditional more likely. Understand? So it is, इन्होंने सिर्फ ये किया कि they have associated the likelihood is associated what I want from the data. I want to maximize the probability of getting the positive class. So they have just associated that with the loss function. Okay, if you minimize the loss function, it is going to automatically maximize the likelihood, the log likelihood, in fact, which is what we typically use. Okay, we typically use the log likelihood in maximum likelihood estimation. So log likelihood is another concept that you need to keep in mind. Yeah, so this is written here. Ye ab aapki baat sahi thi. When we minimize the cost, we are actually maximizing the log likelihood. You're right, but it could be regretful later on. Because देखें, एक चीज होती है innovativeness. Even I don't have that, because we are not trained to think in universities and colleges, unfortunately. We are just trained to get the marks and get grades or get label of some university. If you don't learn, then you have done nothing. So therefore, learn. Oh my God. Yeah. This is not very complicated. In fact, this is the most simplest representation of gradient descent that you will see. Gradient descent is a very famous approach to learn the parameters of the neural network, which are the weights and biases. What happens is that you have a loss function. So this is the equation. This is our hypothesis, if you remember. We have two input attributes, x1 and x2. We have two columns. Bias is a constant which is always there. Okay. So this is the classifier that I have to learn. Y hat is what? Y hat is the output of the sigmoid function, which I am representing it as A, and that is sigmoid of Z. ये तो हमने पहले देख लिया था ना कि first I'm estimating Z, and then I'm putting that in the sigmoid function to get the value between 0 and 1. So that is in here, and obviously this is we mix that up with the loss function. So based on this we derive the loss function. So we will do that in detail in deep learning. So those of you who are not taking deep learning, so ठीक है वो आपके लिए नहीं होगा, लेकिन just try to understand right now कि when you find out the purpose of gradient descent is to converge to the values of weight and biases, which are going to help me learn on the training data. I start with some random values of weight and biases, and I change the weights and biases after every iteration or epoch based on the loss function that I'm getting. मैं क्या करता हूँ, मैं loss function निकालता हूँ, and I back propagate the loss to update the weights and biases. So I keep on doing that until my neural network has converged, or until my logistic regression function has converged, and then it is ready for testing. Yeah, the learning rate is something that you use in neural networks. So you can also put the learning rate here if you want. So learning rate typically is high earlier on, and then we decay it later on. So उसके सारे Python में आपके पास सारे functions बने हुए हैं learning rate में. Yeah, we want to learn the optimal values of W and and B. You see here W is a vector of weights, W2 is a vector of weights, and B as well. Based on this, I'm predicting Z, from which I'm predicting the output of the. So if I want the Z prediction to be correct, I have to learn W1 and W2 and B. That is the training that I have to do. X is already there. I already have X1, X2 in the training data. Okay. So these are the parameters of my hypothesis. So this is coming from the chain rule. If I differentiate the loss function with respect to W1 and I update W1, then I differentiate the loss function with respect to W2, I update W2, and then I differentiate the loss function with respect to bias and I update the bias. I have to do that for each weight and each bias. Okay. So this is a simple example of a chain rule: DL by DA into DA by DZ into DZ by DW1. So all these three formulas I have A in terms of L, I have Z in terms of A, and I have W1 in terms of Z. So I can do the differentiation. And it turns out that if you keep on following this, then DZ over DW1 is X1, and DA over DZ, I don't know what that is. DA over DZ is A into A minus A into 1 minus A, and DL over DA is this form. So now I have to multiply this and this and this to get the value of this differential, based on which I update W1. Okay, so here is the W1 update equation. W1 equals to the current value of W1 minus alpha into DL over DW1, which is multiplication of these three. I'm telling you these things at a very high level. In deep learning, we are going to do it absolutely step by step so that you understand the chain rule perfectly. How is the back propagation done? How is the gradient calculated? But all of these are rates of change. How is the loss function varying with respect to activation? How is the activation varying with respect to the value of Z? How is Z varying with respect to the value of W1? So I'm just multiplying these rates of change together to understand how the loss function varies with respect to, because I don't have a direct equation which can help me reach W1 with respect to the loss function. Loss function ka W1 likha hi nahi hai. So therefore I have to apply this chain rule to get to W1. Okay. So in this way, by using this equation, you will be able to update W1, similarly for W2, similarly for bias. And you do that after every epoch. Epoch ke andar, sorry, after every batch of data. So you can split the, you can split the training data into batches of 100. After every 100 rows, you can update the weights, or you can update the weight after every single row, but that is going to take a lot of time. You should do that when you have less data. But if you have large amount of data, then it's always better to break your data into batches. I mean, we have seen through experiments that using the batches is a better approach than updating after every timestamp, unless it is time series data. अगर आप time series data को neural networks में डाल रहे हैं, then it could be a good approach to update after every time step. But with the typical machine learning scenarios, it is better to update after a batch of data. So इसकी hands on हम कर लेंगे इंशाल्लाह, ठीक है, इसका फिगर नहीं करें, but just try to get the concept, ठीक है? Is this thing clear? कोई question तो नहीं है इसमें? सही है? Absolutely right. अच्छा, let me ask a question. What do you mean by DZ over DW1? And how? Why? I'm not asking how you can calculate that. I'm asking why can you calculate this? What is Z? Absolutely right. That is the hypothesis function. So what do you mean by DZ over DW1? इसका मतलब क्या है? Z की value numerical आएगी या क्या आएगी? Is the value of Z going to be 1 or 0 or a numerical value? It's a pretty simple question. ये equation लिखिए ना, Z equals to W1x plus W2x2 plus B. What is going to be the output of this? It's Z, right? Is it going to be a numerical value or a class label? Huh? Numerical value.
Numerical value.
Everyone sure about that? It's going to be a numerical value. Class label कहाँ से आएगा यहाँ पे? W1 is a weight, X1 is a number, is a real number in most cases. So it's going to be a numerical value. How it is going to be converted to 1 and 0? By application of the sigmoid function. Now you have, so again my question, what is meant by dz over dw1? इसका मतलब क्या है? What does it mean? आप बताएं. In one sentence, logically one sentence, not rate of change of this. वो तो पुरानी definition है जो हमारी maths है. आप, you can explain to me in Urdu. What does it mean? Loss तो है ही नहीं इसमें. नहीं, I'm just asking कि what does this mean? Harim? How is my hypothesis varying with respect to change in weight? W1. When I change the weight, what happens to Z? That is the definition of the differential function. I want to investigate the numerator with respect to change of the denominator. If I change W1, what is happening to Z? That is it. That is the answer. Okay. What is dA over dZ? Find answer from this. Yeah, what we have done here, y hat. What is y hat? Huh? Is the output of the, what is the activation function? Sigmoid, logistic function or the sigmoid, जो भी आप कह लें. So the output of that is y hat, right? A value between 0 and 1. So what do you mean by D? And we also call it A. I don't want to use y hat, मैं उसको A कह रहा हूँ, activation कह रहा हूँ. That's what we do in neural networks, right? So dA over dZ, what does that mean? Yes. So first we are saying that what is the change with W1, W2 and B are bringing to Z? And based on that, we are saying that what is the change with Z is bringing to A? And then based on that, what is the change which A is bringing to the loss function? So we have to start from dZ over dW1. First calculate that. Then we calculate dA over dZ. Then we calculate dL over dA. And then we multiply to find out dL over dW1. And use that to update the value of weights. Okay? Clear हो गई बात ये? सही? You don't have to remember the maths here, just the concept. Okay? Remember कि आपको concept, you must be very clear on that.
Sir, can I ask something?
जी?
Sir, what is the purpose of using gradient descent, and how do we know that we should use it?
In this scenario, when we have a classifier in which we have this particular shape z equals to weight vector multiplied by the x vector plus b. When we are assuming the separating hyperplane or the hypothesis is linear, then we have to use this. Where we have weights and biases, we are supposed to use the backpropagation algorithm to learn the values of weights and biases. There is no other way. So in the case of logistic regression, which uses the logistic function basically, so we use this in the case of all the neural networks. When we have to update the weights, we have to use that, do that using the gradient descent algorithm, which uses this chain rule that we have seen. There's no other way to update the weights in neural networks. So that's the standard way. And the same goes for logistic regression as well. Okay?
Okay, sir.
Okay, question 1, logistic regression is used for?
All of these.
So आपके पीछे, what's your name? Sorry. सरोज. अच्छा यार, पहचाने नहीं जा रहे आप तो यार. हाँ, इसका आंसर दें सरोज. A, B, C और D. ज्यादा A. Zyadatar, what does that mean? What if I say D? Why not D?
Yes, sir.
D. Ramsha probably saying D. Nafisa, what's your answer? So Nafisa is not there. Usman Hassan.
Yes, sir. D over.
डी आंसर है, ठीक है, सही है। और डी, so I don't know what I've been doing for the last 2 hours, but we have been doing, we have been talking about the S curve, right? S curve maps a value between 0 and 1, and we have been saying कि यार we are selecting different thresholds to either map it to 0 or 1 or multiple classes. That's what we are talking, that's what the whole game is all about. That's why we are using the logistic function to find out the probabilities of the classes. So what's the answer? Classification. Regression कहाँ से आ गई? वही हमने यही तो बताया था कि when I showed you that diagram in the beginning between linear regression and logistic regression, that's what it was trying to say कि the problem for which the logistic regression is used has nothing to do with regression. It's called regression for some reason. It is called regression. It's not regression actually doing classification. And clustering का किसने कहा है कि clustering? Clustering में you basically form homogeneous groups of rows. What has that got to do with probability? Huh? Okay, that might have something to do with probability, but not in the sense in the normal way कि आप clustering करते हैं. ठीक है? Question 2.
C.
D, C, and
C.
sorry?
Numerical dependent variable. I think so.
अच्छा, ऊपर हमने क्या कहा है? Is used for classification. तो यहाँ पे numerical कैसे आ गया? How can I make a numerical prediction based on classification?
Categorical dependent variable.
Categorical dependent variable. Is that correct? D? Yes, because what you predict is always dependent variable. ठीक है? G, question 3. Okay, you are predicting whether an email is spam or not. Based on the feature, you obtain an estimated probability 0.75. What is the meaning of this estimated probability? Select 2. Obviously, you have to select 2 because there are 2 classes, spam or not spam. तो कौन से 2 करेंगे? B and D. Is that okay? So positive class 75, negative class 25. ठीक है. अच्छा, oh, sorry about this. So in a logistic regression model, the decision boundary can be A1. ये मैंने बताया अभी.
तो non-linear होगा.
I think it's both.
So non-linear होगा.
आप मुझे बात बताएं कि Z equals to WX plus B. Is that a non-linear or linear? So we are discussing that, right? Where did that disappear? That's not logistic regression. ये अभी हम ये पीछे क्या पढ़ते आ रहे हैं? What have we been studying here? ये क्या टाइटल? मैंने तो I did not even change the slide topic. ये क्या कौन सी regression चल रही है ये? नहीं. I discussed this Z equals to WX plus B, right? This is the logistic regression. I discussed this slide in detail, right? So now I am asking you, okay, this is the decision boundary that we learn also in SVM, right? So is this decision boundary linear or non-linear? WX plus B. This is the equation of a straight line or a straight plane, so it's a linear, right? So the answer should be A. बहुत अफसोस हुआ. I actually मैं भी इस पर surprised हुआ कि वो ये कह रहा था कि इट कुड बी नॉन लीनियर एज वेल. आई डिस्कस दैट, राइट? मैंने आपको इशारा भी किया था कि ये कहां से आ गया. सो आंसर इज सी. Typically we have the linear case, but it could be C as well. I don't know how it could be C. We have to see the math for that. अब बताएं, what's the cost function of logistic regression?
C, both sigmoid and logistic function.
Cost function of logistic regression हमने क्या बताया था? We wrote that down, right? एक minute. Okay, this is the combined cost function. So is this sigmoid function? You think this is sigmoid? ये है ना cost function की shape ये आ रही है, क्यों जा रही है, क्यों जा रही है? Do you think this is the sigmoid function?
Yes.
Cost function की बात हो रही है, not the logistic function. We have option sigmoid function, logistic function, both A and B, none of these. So the cost function is actually going like this. If I make the combined loss function, I think one part was like this, right? And the other part was going like this. Something like this for y equals to 1 and y equals to 0. So I don't know if if I see the formula, if I see the formula for the cost function, so the formula is actually based on the so this formula as theta x is the sigmoid function. So obviously the cost function is the log of the sigmoid. What is the log of sigmoid? It's a log of sigmoid, right? Sigmoid का log लेने से क्या होगा? The sigmoid is the S shape. So how the shape is going to change? Will that remain sigmoid or not? I don't know. Logit बनेगा? So we have minus log. That means I'm taking the inverse of log. If it becomes the Logit function, we need to dig this up. Can anybody Google this right now, please? What is the log of the sigmoid? Shape of the log of the sigmoid. Please Google this up right now. Because sigmoid and logistic mean the same thing. I mean, they are from the same family. So it could be either C or it could be D. Because in this case, we are taking the log of the sigmoid function. What's the shape of the log of sigmoid? That's what we need to determine. Or in fact, the negative log. है ना? The shape of negative log. Bell shape. So then that means if I take the log of the logistic function, if I take the log of the logistic or sigmoid function, it turns into a bell-shaped curve, which is the logistic distribution. नहीं यार, ये कैसे हो सकता है?
No, sir, it will become positive.
And what shape will be? What is the shape of that? What's the? I don't know why they've asked this two values like this. Like taking that a log is a transformation. A log should not change the shape. I mean, if it does change the shape, it should not change the probability distribution. A log is a transformation function, right? So it will remain a sigmoid function. It will remain as that. So the answer should be C. Okay. I mean, this is my logic. You can try to convince me. ठीक है, चलें सही है. चलें आगे चलें. अभी बहुत काम है भाई. हाँ ये तो ये जरा यार ये sorry. चलें, I'll put it here. Why the cost function which has been used for linear regression cannot be used for logistic regression? ये चार हैं. इनको पढ़ के बताएं कि इसमें से कौन सी वैल्यू ट्रू है. So linear regression uses mean squared error. If this is used for logistic, if we use the mean squared error for logistic regression, how will that, what will happen? I mean, I'm getting a value of z, I'm putting that in the sigmoid function, I'm getting a value between 0 and 1. So let's say कि 0 1 आने के बाद मैं, I don't go towards 1 or 0, I just keep that value because I'm getting a value between 0 and 1, right? The output of the activation function is a value between 0 and 1, not 1 or 0. नहीं समझ में आ रही बात क्या आप लोग? What I'm saying is that when you do logistic regression, you have this z, you find out the value of z, we put the value of z in the logistic function. What is the output of the logistic function? Is it 1 or 0? No, it is a value between 1 or 0 on the S curve. So अगर हम कहते हैं कि यार हम linear regression error formula use करना है, we do not, हम threshold लगा के उसको 1 0 पे नहीं लेके जा रहे हैं, सही है? That's what we're doing right now, right? If I am using the concept of linear regression in logistic regression of the error function, I don't use that error function of the minus log type. What I say is कि अच्छा, I have the value from the output of the activation function. Let's compare that with the actual value and find out the error. Why is this not correct? देखें, convex or non-convex, I will tell you again कि convex function is something like this. It is very easy to find out the global minimum, minimizing the cost function. If the cost function is convex, then it is very easy. If the cost function is non-convex, yes, it is going to be a wavy thing, and it is going to be difficult to converge to the global, to find out the global minimum. So I might stop here and say कि यार यही answer है. That might not be the answer. So the fact के then मेरे ख्याल में तो आंसर ये है कि if I use the concept of linear regression in here, then the cost function is going to be non-convex, and it might not be easy for me to find the global minimum. Therefore, I use the logistic regression because उसका जो cost function की shape आएगी, that is a convex shape. If you take the, you see what हमारा किस तरह का आ रहा था, एक ऐसे आ रहा था, एक part ऐसे आ रहा था, एक part ऐसे आ रहा था, ऐसे था ना? So this is a convex shape. It's easy for me to find out the minimum in this case. But if I use the logistic linear regression mathematics, then I will have a boundary which is non-convex. So क्या आंसर होगा फिर? Then it will be a non-gradient. हाँ, ये the C will be the answer. सही है? The answer is C. Because if I use that for logistic regression, then the cost function will be non-convex, and gradient descent is not able to find out the values of the globe. हाँ, तो ये गलत लिखा हुआ है. A आंसर, ठीक है, सही है. हाँ जी, क्वेश्चन 7. ये बहुत आसान है. हाँ, कौन? द ईमेल स्पैम, सही. ये तो ठीक है ना, तो बहुत बच्चों वाली थ्रेशोल्ड भी बता दिया उसने. अच्छा, व्हाट इज द हाइपोथेसिस ऑफ लॉजिस्टिक रिग्रेशन? ये अच्छा सवाल है बहुत. There is a logical flaw to it. How can I limit something between minus infinity and infinity? I limit in a range, right? Now this is, आप मुझे बताएं कि what can be the potential answers? Let's first figure it out step by step. इसको eliminate करते हैं. कौन से दो आंसर्स हैं जो कि which cannot be there, which cannot be the answers? हाँ, C और D नहीं हो सकते, B और D नहीं हो सकते. एंड तो हाँ बताइए, कम ऑन जी. रमशा, give it a shot. Which are the two things that we need to eliminate here?
Sir, C and D.
मुझे तो कुछ समझ नहीं आया.
Sir, what about B and D? B and D.
Minimum cost क्या हो सकती है? What can be the minimum cost? कहाँ क्या मैंने तो कुछ नहीं लिखा. देखिए it's good that you are thinking. Cost equals to infinity for h theta x equals to 0. ठीक है. So cost can go towards infinity in the case of logistic regression. सही है. Agar if you take this logic, then the purpose is to limit the cost function between minus infinity and infinity, but that just does not make sense because that was the extreme scenario, which is never going to be there. ठीक है, वो कभी होगा नहीं कि 0 हो जाए या पूरा का पूरा 1 आ जाए. Let's take the normal use case. If I take the normal use case, then what two things we can eliminate? Let's assume that the minimum cost can be 0.
Sir, I
That's
think
what
A should
we
be the
want to go
answer.
to a cost which is 0, right? So the minimum cost has to be 0. So the potential answers are A and D. Now, which one is the right one?
Sir, I think A is the right one because in logistic regression, we see true and false, 0 and 1 values.
Yes, it is possible K is the right answer, but actually to find this out, what we have to do is this formula for the cost function, we have to try out different values and see whether the value is converging between 0 and 1. I personally think it is going to remain under 1, sorry. So A is the right answer. The minimum value of the cost is 0 and the maximum value is 1. एक सेकंड जी. हाँ, ये भी बात सही है कि वही 100 के the log of the cost function, log of the sigmoid is log is just a transformation, so it should remain to retain the characteristics of the sigmoid function. हाँ, but the real way to find that out is to actually find out on the graphing calculator or online. अगर इस तरह का सवाल आपको आवरली में आ जाता है तो you should be able to tackle that. तो आप गूगल से भी देख के बता सकते हैं. ओहो, which one is not true? जब तक न्यूमेरिकल्स नहीं करेंगे तो फिर इंटरेस्ट नहीं पैदा होगा ना. Just do this. This is just 2 questions. The value of the sigmoid function always lies between 0 and 1. This is the answer, right? Which one is not true? ये तो true है. ठीक है. Logistic regression is used to determine the value of a continuous dependent variable. It's not saying categorical numerical. वो कह रहा है continuous है या discrete है. Continuous ही होता है, तो this is true, right? What about B? We don't output the weighted sum of inputs directly, but we pass it that can map any real value between 0 and 1. Acha. If we take the weighted sum of inputs as the output, as we do in linear regression, the value can be more than 1, but we want a value. That is why linear regression can't be used for classification task.
Sir, I think D is the right answer because it is saying continuous dependent variable.
नहीं, regression में dependent variable numerical होता है. नहीं, it is not saying कि वो categorical है या numerical है. It is just saying a continuous dependent variable. So it is a continuous जो हम करते हैं. That is true. We have to distinguish between A and B. Logistic regression is generalized in the sense that we don't output the. नहीं. B is the false answer because यहाँ पे वो कह रहा है कि logistic regression is nothing but linear regression. We just pass it through a filter. We don't pass it through a filter. We learn the equation of a line. ये तो हम linear regression भी करते हैं. But in linear regression, we don't have these weights and biases. We have, we can have, no, we can have this in this formula. In a multiple linear regression scenario, we can have such a formulation. If we take the weighted sum of inputs as the output, as we do in linear, the value can be more than one, a value between. No. I think A is the answer. I think यहाँ पे वो is talking about something really, really out of the moon, out of the blue. It does not make sense to me. If you take the weighted sum of inputs as the output, what is the weighted sum of inputs? W1 into X1 plus as the output, as we do in linear regression, the value can be more than 1. So that is the prediction, right? But we want a value between 0. No. This is the answer. This is false. The output of the linear regression has everything to do with the output of logistic regression. The same kind
E
of
should be the right answer, I think.
Let's create a new entry, E, none of the above, and just select that. Okay, I will leave it to you. अगर आप कहाँ से आ गया?
Hello?
अच्छा, कंटिन्यूअस की बात कर रहे हैं. ओ, हाँ. A discrete dependent variable. You mean a label, class label. You mean a class label. हाँ, ठीक है. But this I'm not comfortable about A. अच्छा, हाँ. With one perspective, you can say कि A is also true. कि logistic linear regression कभी भी is not always going to give you a value between 0 and 1. So in that sense, A is also correct. So ठीक है, D is the answer. In a logistic regression, if the predicted logit is 0, I think I just sorry about that. Oh, sorry about that. If the predicted logit is 0, what's the transformed probability? ये predicted logit. Logit क्या था? What was the logit? It was the quantile function. Do you remember the formula for the logit function? No, that was the logistic function. We're talking about the logit function. Logit function has this formula, log p over 1 minus p. So if the probability is 0, 0 over 1 is 0. Log of 0 is 1. Do we have 1 here? I am sure इतना अच्छा 1 लिखा हुआ है तो ठीक है, let's mark 1 if it is simple for us. हाँ, नहीं, log of 0 1 नहीं, log 1 0 होता है. हाँ, तो then that means k infinite. So if the value of x is infinite, then what happens to the logistic function? So logit function. So 0 equals to log p over 1 minus p and solve for p. 0 equals to log p over 1 minus p and solve for p. That's what we have to do. Okay, so वो निकाल लीजिएगा फिर. अच्छा, if you're not able to solve, then just write the equation. जिसमें आपको नंबर मिल जाएंगे. ठीक है सर. 0.5 होगा शायद. In this case तो आप वो try out करके भी देख सकते हैं कि अच्छा हाँ यार directly try out कर. Log of 1 0 होता है. How to make p over 1 minus p as 1? Log of 1 0 होता है ना. तो p over 1 minus p को how you make that 1? So simple, yaar. It's most simple thing. 0 equals to log p over 1 minus p. What should be p? Log of 1 is 0, right? How to make this 1? इसको 1 किस तरह बनाएंगे? Let's make it 0.5. If p is 0.5, 0.5 over 0.5 is 1. Log of 1 is 0. So the answer is 0.5. Mathematics करने की जरूरत ही नहीं है. Innovative, भाई. Get innovative. हम भी साथ साथ ही सीख रहे हैं. अच्छा, बस ये 3 रह गए हैं just. Okay, suppose you have trained a logistic regression classifier and its output on a new example X, a prediction h theta x equals to 0.2. So the output of the logistic function is 0.2. This means that by default the class is 1. So when I say the prediction is 0.2, then that is actually the predicted value for the positive class. So the answer is our estimate for P y equals to 1 given x comma theta is 0.2 and नीचे वाला भी is the same thing, ठीक है? Because it's just 1 minus of that. Oh, so suppose you have the following training set and fit a logistic classifier this, right? So I have two classes. So the red one is 0 class and this is 1. Adding polynomial features. Acha, yeah, this is you are learning. So in this case, what we are having, we can add these. ठीक है. This is like we saw for, I don't think so. अभी regression अभी हमें करना है, but we have like I can have polynomial regression in which I can increase the order of the equation, like cubic equation, quadratic equation, or fourth level power equation. So in this case, आप देख रहे हैं कि we are into the square. But we could add the polynomial features to better fit the training data. That's also an option, but that is like more complicated. इसको इतना वो नहीं है. We will have j theta greater than equal to 0 at the optimal value of theta. It is possible कि overfitting हो, but then you avoid that using cross validation. ठीक है? Or another technique. अच्छा. Now ये जरा बता दें आप. Yeah, last step for logistic regression, the gradient is given by. So let's. This is what we have done, very similar to that. So if I find out the, okay. So I will just, I will have to share that. Okay, so just put it down here. So the logistic regression, the gradient is given by d over d theta j. But the theta means w and bias together. Theta means all the parameters together. So I know I have to differentiate that. So it is given by finding out the difference between the sigmoid output and the actual output, multiplying that by xj, which is the x value. This is one way to write that. Okay. Which of the following is a correct gradient descent update for logistic regression with a learning rate of alpha? We saw that alpha, right? Okay. So अब बताएं आप. I am updating theta, which could be either W1, W2, or beta, whatever. Bias, sorry. इसमें से कौन सा सही है? So to get the answer for that, I think we have to see this. Yeah, so we have to see this one. So what is the answer when we multiply DL over DW1 was what? A minus 1 into X1, which is X in this case, that XJ जो है ना वो ये वाला है. So A minus Y into X1 multiplied by alpha. So do you see any similarity to that? What is A? अब तो मैंने clear कर दिया. A is the activation function. What is that? What is the activation function we are using? Sigmoid function. Where can you see the sigmoid function here? Third, A minus Y multiplied by X. That's what we saw here, right? When we were updating, ये देखें, इन तीनों को multiply करने से we got this one, A minus Y into X1, and that is what we are using in update. Okay, so the A is the is this one. This is A, this is Y, this is X. Finish. Okay. Okay, so now just a few very quick slides regarding the joint probability distribution. ये थोड़ा सा मुश्किल लिखा हुआ है. Just remember कि when I have a single random variable, so we are talking, अभी तक we have been talking about a single random variable. It can follow some probability distribution function, right, or a density function. But I can also have two variables together, 3 together, 4 together, 5 together. Okay, so that is called the joint probability distribution. And this is one of the examples of the shape of the distribution or the density curve when we have two variables. But in the training data, you can imagine that if we have 5 or 6 numerical variables or KPIs in your training data, then that is a joint distribution of 5 or 6 variables together. That is defining your training data. Because remember one thing, in machine learning, string data does not mean anything. So in the end, you are supposed to convert string to numerical values or just delete them. We don't have anything to do with strings. Okay? So just see this quickly. So this is a discrete probability distribution function, which is called the probability mass function, if you remember. Just one variable and we have discrete outputs. So, but sometimes we are interested in the continuous case. For example, year in college versus the number of credits taken. I have two variables. Number of cigarettes smoked per day versus day of the week. Time when the bus driver picks you up versus quantity of caffeine in the bus driver system. Dosage of a drug in milliliter versus blood compound measure percentage. So all of these are examples for studying the human behavior. I'm not motivating you to do anything. ठीक है? ये इसके जब वो आप बीमार हो जाते हैं, लंग्स वगैरह की प्रॉब्लम्स आते हैं, फिर वो डॉक्टर्स पे स्टडी करते हैं कि क्या इफेक्ट आता है. So in general, if x and y are two random variables, so unka jo combined is called a joint, and we have a table like this, a very simple table. So y can take on values 1, 2, and 3, and x can also take on values 1, 2, and 3. सही है? For example, ये आप देख रहे हैं कि it should disappear here, right? So in this case, I can have such a PDF. So this is a joint PDF. ठीक है? तो I have to specify the values of both the variables to get the value of a probability. So these are probabilities, and this can be a function, the shape of the function. Okay. Sorry for that. So this is an example. We can have a joint PMF or a PDF, depending on dono random variables, are they discrete or continuous. So we can have both. So for example, when you're talking about plastic cover for CDs, so we can have a variable regarding the length and the other for the width. So the distribution can be something like this. So there are 6 possible pairs. So length can be this, and so the PDF is defined in this way. So the combination with the highest probability is this, with the lowest probability is this, and the joint mass function can be represented in this way. So it's pretty simple right now. अच्छा plan है. लेकिन I will just tell you about the marginal, just the last slide. ठीक है? Marginal, what does it mean? Yeah, you are given the joint, but you are only trying to find the probability of one of them. So you have to add the probabilities for all the values of that particular random variable across the values of the other. For example, if I say, okay, what is the probability that the length is 129? I'm not talking about the width of the CD cover. I'm just talking about the length. So then I have to sum up across all the, so these are called marginals in the joint probability distribution. A marginal, we call them because they are found in the margins of the PDF table. So yeah, so for example, if I sum up across 129, so 0.12 and 0.08 is going to be 0.2. So 0.2 is going to come here, which is the margin of the table. So that is why these are called marginal distributions. Okay, so just remember this concept, right? It's very easy to estimate. For example, here we have 0.2. So I can find 130, 131, 15, 16 separately, and all of these will be marginals. So from the joint, I have two particular conclusions. One is the marginal distribution. The other is the marginal. Joint से दो चीजें आती हैं, marginal and शाबाश. Who can tell me? Very easy. When we have two random variables, what is the distribution we do? Conditional. Y given x. One is the marginal, given the values of all the variables. The other is the conditional. For example, I can say, what is the value that x equals to 129 given that y is 15? That is 0.12. So yeah, good. We're talk about in more detail. Okay, so in the next class, we're going to be touching this topic in detail because we have to do the Gaussian mixture distribution, which is the distribution of multiple variables together, and it's Gaussian. And I will also give you the quiz, which you will have to complete within one day. and the assignment is ROC, but you can extend the time for assignment as much as you want. I have no issues. Assignment is I will just put that on LMS. Okay. For the first assignment, I'm going to extend till tomorrow night. And for the ROC one, we can go till next Tuesday. And or maybe next Thursday if you want, it's not a problem. Quiz will be there. So quiz, please don't ask to extend the quiz deadline, please, because it's an exam. Officially, I'm supposed to take the quiz here. नहीं ले सकता. Okay, guys, online guys. ठीक है. Any questions?